We are in the middle of talking about whether functions are continuous or not. And we're mainly emphasizing looking at graphs of functions. And you looked at the graph of a function, it's very easy to see whether it's continuous or not. But I'm digging a little deeper and explaining that there are two kinds of functions that we can have that will oftentimes end up being not a continuous function. Rational functions for sure all the time. But the second category is called piecewise functions. Sometimes piecewise functions will be non-continuous. So let me first take a few minutes and explain to you what piecewise functions are, which we need to do because we're going to deal with piecewise functions in calculus. So piecewise function, the name sort of gives it away. Piece. It's almost like it's a function or graph with two or more pieces. That may seem so strange. Easiest thing is, let me just simply give you an example of a piecewise function, and we can look at the graph, but I don't think it'll be too difficult. So here's how it looks. The look is very different. So we're going to say my function equals, but instead of just writing some kind of expression, I'm going to put like this big, like a brace. What I'm going to do is I'm going to say f of x, the function equals x squared if x is less than 2. Let me just write this out, then I'll explain it. But then below it, I'm going to say f of x equals 1. I'll do this, less than or equal to if x is greater than 2. All right, what in the world is this? You know what this is? This is almost like taking two separate functions. Here's like the first function. A lot of times we call this the first function. Here's the second function. And you're putting them on the same graph. And it's almost like you're just smashing them next to each other. And if you look here, this information, these inequalities here, it gives you what I call the transition point. So let's take a minute to explain what this means. So say you're given this function. Easiest way is you're told this is the function, and you're asked, what is f of 0? Well, first you might look at this and you say, well, f of x, if I look at the first function, it's x squared, but then also f of x can equal 1. It's like f of x, it's like there's two different equations here, two different expressions. Which one do I apply? Well, the key is you have to look here at what we call the conditions. You notice these conditions are broken up and defined by the value of x. So look at this. If x is less than or equal to 2, that means you're going to use this function. If x is greater than 2, then you use this function. So these conditions will tell you which function you need to be using. And you notice, of course, the conditions, they both center when x is 2. And that's why I call this the transition point. It's almost like if x is less than 2, matter of fact, I'll make a rough sketch of the graph. You go here, so here's x, here's f of x. If x is less than or equal to 2, then my graph or my function is gonna be x squared. But as soon as I get to 2, and as soon as I start going to the right, where x is larger than 2, my function changes and is equal to this. So it's almost like 2 is the transition point. I normally don't do this, but because it's almost like, it's like I'm going to have 2 functions just right next to each other. To the left, this is going to be my function, x squared. F of x equals x squared. Well, the graph of that, if x is 0, the function 0. If x is 1, the function, if I put in 1 for x, you get 1. If I put in 2 for x, you get 4. Now you notice x less than or equal to 2. When I'm here at 2, this first function is still in charge. So when I'm here at 2, so this is an asymptote. Just so you know, I'm just sort of drawing this line to show you where the transition point is. When x is 2, now if I were to keep the graph going over here, when x is -1, so what I'm going to do is, this ends up being a parabola, and I'm going to draw this parabola, but you know what? When I get to x equal 2, I have to stop. Because up here it says, this is the function when x is less than or equal to 2. This part of the graph is when x is less than or equal to 2. As soon as I get to 2, the function is going to change. Because this says now if x is greater than 2, it's over here. So back to my question. Well, let's graph this second part, and then we'll start to answer some of these questions. So when I get to 2, when x is greater than 2, the function equals 1. Here's 1. So what I do when it's at 2, now I'm going to draw an empty circle. The reason the circle is empty here is because this function does not apply when x equals 2. It's when x is greater than 2. So you remember when you're graphing, if you don't include the point, you put a 0. See here, it's a filled in circle because for this part of the function, it's x less than or equal to 2. So I include the 2 for this first part of the function. For this one, it's not. Now, what's it look like when you have f of x equals 1? Well, that's actually the equation of a horizontal line. And so it looks like this. So this is a piecewise function. So what it really is, it's like 2 totally separate different functions sort of smashed together, and it looks like this. So the key is these conditions here tell you where the change is. In other words, when x is less than or equal to 2, so I go to 2, my transition point, everything to the left of the transition point, the function follows x squared. However, when I get to the transition point and I go to the right where x is greater than 2, the second function then is in control. So If you're given, and this will happen in class, if you're given a piecewise function and you're asked a question like this, f of 0 equals what? Like I said before, initially you think, well, which function should I use? Which expression should I use? Well, the key is you look at the conditions. If x is 0, which of these is correct? This function is saying use this function if x is less than or equal to 2. Is 0 less than or equal to 2? Yes, it is. So you know what I'm going to do? When x is 0, I use the first function. What if I said, what is f of 3? First thing you have to do is you look at your value of x and you figure out which of these functions applies. And it all depends on your conditions. So since x is 3, it's got to be down here because this is the function when x is greater than 2 and 3 is greater than 2. So for this one, turns out I use this second and I say f of 3 equals 1. And if you look at the graph, it makes sense, right? Here's x equals 3. So I'm at this point right here. The function's 1. For this one, f of 0 is x right here. I'm on my function, the function 0. Here's one that might be tricky. What about f of 2? The reason I say it's tricky is because 2 is actually the transition point. It's where the function changes. So the key is you have to look at your conditions and you see which one of these functions actually includes 2. And since this one is x less than or equal to 2, that means if x is 2, you're in here. You know, down here is x greater than 2. So which one of these includes the value of 2? This first one. So you would have 2 squared, which is 4. And it makes sense when you look at the graph, because look at the graph here. When x is 2, it's 4. Now I sort of did this graph here, but if you look at it officially, once again, it looks like this. So it's very obvious. You know, you're coming along here with a nice parabola, you get to here, it just stops. And then it jumps down here and it's like a horizontal line. So obviously, a couple things. First of all, this is not a continuous function, right? If I'm trying to trace out the function from left to right, I get to here, I have to jump down to here to keep going. So the idea is that it's not a continuous function. There's a break, there's a gap here. But the thing you also realize is this is a piecewise function. And what happens is, obviously, x equals 2 is the transition point where the function changes here. The function is x squared, nice parabola. Once you get to 2, the function changes to where it's just a number and becomes a horizontal line. Now, what's interesting, what if I would just change one thing here? I'm going to do another piecewise function. It's going to almost be the same with one change. So my first function is x squared. I'm going to keep all of this the same. X squared if x is equal to 2. Then the second part, here's the one change I'm going to make. Instead of 1, I'm going to make it 4. So the function is going to equal 4 if x is greater than 2. So the transition point didn't change. First function didn't change. The only change I made was the second function. Instead of being the number 1, I changed it to 4. So here's the function. If I look up here, here's the graph when the function equals 1. Now, for this new one, if I were to graph the second function, instead I would go up to where the function is 4, and then I would draw my vertical line. As a matter of fact, I graphed it out here. So for this second piecewise function, it actually looks like this. So once again, you've got your parabola. When x gets to 2, it stops. The function changes. The function becomes a horizontal line. And in this case, for this one, it's f of x equal 4. But the interesting thing is, if someone said, if they gave you this graph and said, is this a continuous function? Well, can I trace out the whole function without ever lifting my pen off the page? I go here, I go here, I go here. I get to here. This is the transition point. But you know what? Turns out the transition point, the two functions meet at the transition point, and I just keep going. So this is, in fact, this is a piecewise function that is continuous. Here's almost the exact same piecewise function, and it was not continuous, because when you go along here, when you get to the transition point, you had to hop down here to keep going. Well, for this one, all I did was basically take this part of the function and moved it up here. And now I have a piecewise function. When I get to the transition, I don't have to make a hop or a jump. There's no breaks. I mean, it's a different function, but it just keeps going. So you would say this is a continuous function, and this one is not continuous. So that's why I said before, typically when we're looking at continuous functions, radical functions where you got a fraction, I think it's almost always going to be not continuous. Piecewise functions, it depends. Some piecewise functions are not continuous because at the transition point, there's a break, there's a gap. But then some piecewise functions at the transition point, the two functions meet and they are continuous. Matter of fact, just to give you a little more practice on piecewise functions, I did one more. And this is actually, so this one had like 2 parts, 2 functions. There's 2 pieces to this piecewise function. But sometimes you can have even like 3. So let me just write out the equation of the piecewise function, and then I can show you the graph. So this is going to have 3 parts actually, which means there's going to be 2 transition points, 2 different places where 2 totally different functions have to meet or are squished together. So the first one is f of x is going to equal x plus 1 quantity squared. Here's the condition. If x is less than or equal to 0. What this is basically saying, if x is either 0 or a negative number, this is like the controlling function. So even on my graph, if we sort of just, this part, of the graph is going to be controlled by this. Now the second function is going to be the function equals 1 if, look at this. This is a two-sided, two-sided inequality. This is basically saying this is going to be the function if x is greater than 2. Sorry, if x is greater than 0 or less than 2. In other words, whenever x actually, it's like this. Sorry about that. So here, the function applies here when x is greater than 0 or less than or equal to 2. So in other words, if x is greater than 0, like a half, 3/4, 1, 1.5, all the way up to and including 2. So if x is, like I just said, it's 1/2, 1, 1.5, 1.75, 2, then the function is going to be 1. So it's almost like, here's 2. So the first function is for here. The second function is going to cover here. Actually, let me draw this because I don't like how that turned out. So it's almost like first function is all over here. Since x is 2 is here, here's where the second function is in charge. And then my third function, the function is going to be negative 1/2 x plus 2 if x is greater than 2. So then when x is greater than 2, the third function. So just for fun, what if you were given this and you're asked, what is f of -1? First thing you have to do is you look at your value of x and you go to your conditions and figure out which one of these applies when x is -1. Well, this one says if x is less than or equal to 0. So this one, it's the first function. So you plug in -1 for x and you get 0. So in a minute, when I show you the graph, when x is -1, the function should be 0. What about if you were asked, what's the function equal to when x is 1? First thing you do is see what's my value of x. X is 1. Got to figure out which condition applies. X less than or equal to 0. Well, that's not true. How about x greater than 0 and x less than or equal to 2? Since x is 1, now I'm in this second function. The second function simply equals 1 all the time. So when I go to my graph, if I go to x equals 1, the function should be 1. What if I'm asked, what is f of 4? So once again, with x being 4, go figure out which of these functions applies. And in this case, this last one says, this is the function you use if x is greater than 2. Well, since 4 is greater than 2, this is what I use. So I plug in 4 for x. So this is -2 plus 2. It's actually 0. It's interesting. So I gotta look at the graph when x is 4. Now let's just, for fun, look at their transition points. There are actually 2 transition points, right? The first one, these first 2 functions meet when x is 0. Then the second, third functions meet when x is 2. So for the first transition point, f of 0, which one of these applies? What's this one? because this includes 0. So when I put in 0, 0 plus 1 is 1. It's like it's that. And then the second transition point is 2. So what does f of 2 equal? Well, it turns out this middle function includes 2, so it's just going to be 1. So let me show you the graph of this function, and then we'll just look quickly and see if our calculations were correct. The graph of that function looks like this. See if this sort of makes sense. Maybe we can see this a little bit. Here it is. X less than or equal to 0. This is like a parabola. So you can see here. And once you get to 0, which is my first transition point, it's pretty obvious. The graph changes. It's made a parabola. Now, when x is greater than 0 or greater than or equal to 2, it's a straight line where the function equals 1. So like this is the first function. This is the area for the second function. Then the second transition point is when x is 2. And then this is like a linear equation. So this is the function. This is the graph of -1 of x plus 2. So of course, these go on forever. So this is the graph of this piecewise function. Just for fun, let's check out our points. We said, what is f of -1? And we said it should be 0. Well, -1 is right here. And yep, here's my x-axis. So the function is definitely 0. And we said, how about when f of 1? Well, x equals 1 is here. It's that point right there. The function equals 1. Yep. How about when x equals 4? What does the function equal? Actually, 4 is off my graph. It's out here someplace, and we said it's going to be 0. It looks like it's possible, right? Because it's heading down here. Then we did the transition points. F of 0. 0 is a transition point. We said it's 1. Now here, it doesn't really matter because it turns out at the transition points, the different functions meet. So at f of 0, it's obvious that the function is going to be 1. And then at f of 2, the function is still going to be 1. So now, if you were given this graph, this is a piecewise graph of 3 parts, and you ask, is this a continuous function or not? You would say, even though there are 3 parts to this graph, at both transitions, the functions are connected. So this is, you would say this is a continuous function. And once again, I made one change. If I did it again, what I did here, instead of having the function equal 1, I made the function equal to 1/2. That's the only change I made. But when you do that, then what happens is this middle function, instead of being up here at 1, which causes all these parts to be connected, you drop it down to 1/2, and all of a sudden, you have a couple breaks or gaps on your transition points. So if you were given this graph and they said, is this a continuous function? You would obviously say no. It's not continuous. All right, so the idea of continuous functions is not very difficult, especially when you're looking at graphs. I mean, actually, you know what? If you were given this problem and asked if this is continuous, we will see how to determine that. It takes a little bit of work. But when you're given a graph, 5 seconds of looking, and it's obvious whether it's continuous or not. So the big picture, continuity is pretty easy to see on a graph. But I decided to go and take some time, and this gives us a chance, especially to talk about what piecewise functions are and also what rational functions are. So I have a little bit more to review before we're ready to dive into full-blown calculus. A few more things to talk about, and then we'll be ready to go.